All right, so here we are. If my camera works, we're going to do a little hydropower theory for our micro-hydro project. So I'll start kind of generally, and then I'll get into the specifics. And Ryan, you've probably seen a lot of this previously. And thanks for kind of taking the lead on getting through the theory. But so here, let's just go with this. So micro-hydro theory. And we're just going to start with the conservation of energy. So conservation of energy is the first law. And I already heard Ryan talk a little bit about converting mechanical energy into electrical energy.
Yeah, we just went real briefly.
Yeah, and that's the whole point. So I'm just going to write out first law. And the first law just says that the change in energy over the change in time equals 0. But just so you can't create energy, can't destroy it. Maybe you can turn it into mass, but we're not doing relativity, so we don't have to do the whole E equals mc squared thing. But what we're looking at here is, well, first of all, what kind of energy is hydropower, hydro energy? I'll just ask Jasmine if she knows the answer before everyone chimes in. Any guess what type of energy it is? Yeah, just give me a wild guess. What's even just the first thing that comes to mind is fine.
What was the question?
What type of energy hydropower is?
Force or
Okay.
energy?
What's that?
Energy? Something?
Kinetic is one way to do it. Yeah, and that's exactly right. It is kinetic energy, and it's also right in a sense. It's potential energy. That raindrop was up in the sky, and let's just look at both of those really briefly, just so energy can equal mgh, and we can even do it for one little droplet of water, right? So if here's the surface of the Earth, here's your water droplet up there, it has some mass, the force of gravity is pulling it down, and it's a distance h from the ground. So that's how much, and what's driving that? How'd that water molecule get up in the air?
Evaporation.
Evaporation. What made it evaporate? I mean, why?
Heat, energy.
Yeah, from...
Sun.
Yeah, so the sun, little photon came down, got trapped in that water molecule, got it all jiggly to the point that it said, hey, see you later, ocean, see you later, ground, see you later, whatever. Drop of sweat on your brow, doesn't matter where that water came from, it's up in the sky because sunlight came down and forced it up there. Okay, so that's our potential energy. And so we can write that down as potential. Yeah, just put a P for potential. Okay, now that droplet is going to then fall to the Earth. It's then going to hit a river, and then it's going to be cruising along in the Clark Fork, for example. And I think Jasmine, you might have even said kinetic energy, and that's correct. So E kinetic equals 1/2 mv squared. So you'll notice with potential up here, you've got a height involved, but now we're down in the river, and okay, so the height is changing a little bit, but in general, at least with your technology, the change in height through your microhydro is going to be insignificant. What we're getting instead is this velocity. So you have some little mass, and again, it could be a single water molecule, it could be a liter of water, and we're going to get to that when we get into the details, but now it's moving with some velocity horizontally, and that's where the energy comes from. So both of these, and this is back to the original question I was asking for, both of these are mechanical.
That's what I was thinking.
Yeah, so there you go. So mechanical is one of the broader forms, and there are different subcategories within mechanical. Potential is one, kinetic is another one. Okay. And then we'll just really quickly note that in terms of the unit analysis, and this is something you can go back into and check all the time if you're not sure what units you're dealing with. Mass has units of mass. Gravity has units of length per time squared, and height has units of length. So if we multiply mass by length over time squared, ml squared over t squared. That's energy, no arguing with that. Same down here. Mass, of course, has units of mass. Velocity has units of length per time, meters per second, miles per hour, what have you. You square them both, and so it works out. And so we just demonstrated that we're still dealing with the conservation of energy. Okay, so now the question is, for our particular technology, and what we're trying to do here is we're going to have, in any one of these things, you're always going to have some kind of what's called a control volume. So you start here, and we can call this A for area in, and we can call this A for area out, and then and they might be different, and you're going to have to sort of look at your two technologies and say what is the cross-sectional area of something coming into this system? What's the cross-sectional area coming out? And that might, and we'll iterate on that as we get there, but I'll just show you in general how to approach that problem. Now, tell me, if I get a bigger area, am I going to have more power or less power? More, right? I mean, that's why dams get bigger, that's why wind turbines get bigger, that's why solar panels get bigger, to get more power, obviously, so the more area. Now, we're also going to have, as we said a second ago, we're going to have velocity coming in. There's another way, and we know that the units of velocity are meters per second, or length per time. We're also going to have, and a lot of times this is written as Q for flow. And this is where it gets a little bit confusing. The poor letter Q gets overused. Q is sometimes meant to denote heat. In this case, we're using it as mass per unit time. So I showed you already that the first law says that the change in energy per change in time equals 0, or energy cannot be created or destroyed. And there's another way to look at that, is to say that let's just shift gears briefly from energy to power, and I'll show you exactly what I mean by that. So power is actually the change in energy, and this is maybe a little bit confusing, but hopefully it'll become clear if you go back and watch this video again. The change in energy per change in time is power. Well, what's that mean? We know that as that raindrop is falling from the sky, it's releasing power. It's giving power from the potential energy into kinetic energy. It's going to be the same with water moving through your system. So change in energy per change in time is power. In our case, and I think this is where you're going there with it, Ryan, was for a hydrothermal system, the power is equal to the pressure, in some sense, times the flow rate, Q. And where does the pressure come from? Well, it comes from the fact that if we suddenly built a wall in the river, obviously that would create pressure as a dam. So there's always just a little bit more pressure upstream pushing things downstream, and it's continuous. But there is pressure there in the river. So you're going to have some pressure here as well, and you're going to have some pressure down here. So I'm just going to call that pressure in, and I'm going to call this pressure out. So I can also have a velocity in, and I'm going to have a velocity out, and then I'm going to have also a Q in and a Q out. Okay, so here's the question. Your Q in versus your Q out, and again, let me write down what Q is. So we already know that the dimensions of velocity are length per time. We know that the dimensions of area, obviously, are length squared. How about the dimension of the flow rate, Q? And again, this is the volumetric flow rate. So typically you give it as like gallons per minute would be one. So, and there's two different ways to do it. You can either do it as gallons per minute, you could do it as cubic meters per minute, you could do it as cubic miles per second. We're talking the draining of the ancient Lake Missoula, cubic miles per hour. But I think what we're gonna just do here is write it out as just so we can quickly get to energy. I'm going to write it as kilograms per second, or mass per time. So I've written both the units right here, and I've written the dimensions right here. So sorry for sneaking those units on you, but eventually you need to get to units so we can turn this thing into watts. All right, so if we know, getting back to power and the relationship between power and energy, we know that energy has dimensions of mass times length squared over time squared, and we know that power is energy divided by time. So let's just keep going here and write down that the dimensions of power equal mass times length squared over time cubed. Okay, so now we're getting somewhere, because we can see we've got the area in here. That's kind of looking like a length squared. We've got mass sitting right there. Okay, now that's kind of tied in with Q. We've got a velocity. We may or may not use that, but now we just have to tie all these guys together. So let's think about the best way to get at power. Because what we're actually going to do, well, what's the goal? The goal is actually to take the mechanical energy and turn it into electrical energy. Now, so I need to draw kind of one more arrow on this system, and so what's going to be coming out of this thing is, I'm just going to write it down as this, power sub, I don't think I've used an E yet. I used P for potential, I used K for kinetic. I'm going to use, how about just a little e here for electrical, because we're going to have electrical power coming out. So I've already showed that in the case of hydro, your power is pressure times volumetric flow rate. In the case of electricity, it's going to be volts times amps. And so that's the part that we're going to pull off of this. So what we're going to see in our overall equation is that power electric should equal the power, let me make sure we do this right here. So the power in is going to be greater than the power out. We're going to take some of that power out of the water. So here's your power in minus power out. So now it's just going to be up to us to figure out how much mechanical power is going in, how much mechanical power is going to come out. The rest, if we do a good job, is going to turn into electricity. Ultimately, a lot of it becomes thermal. We're going to hear this thing running. Some of it's going to be acoustic. And maybe we can just write that up as power, I don't know. Well, I'll just go ahead and write them out. P sub T, that's going to be thermal. There's a little bit of that. You're also going to have P acoustic, coming out too. You'll hear it. You'll hear it. You know, if we didn't have this thing in the water, it would not be. It's not going to be that noisy, but there'll be a little bit there.
Paddles.
Yeah, right. So again, that's back to your whole conservation of energy. Can't be created or destroyed. So thermal power, acoustic power are also coming out. And technically, acoustic power is still mechanical, and you can debate whether or not thermal energy is mechanical or not, but it happens to be, you know, part of it. Okay, so we'll just kind of sneak those in here as power acoustic plus power thermal, and I'll just kind of put those in little dashes because unless you want to get super fancy and measure the temperature of the device before and after and go out there with a a microphone in some type, we're just not going to get to that. So, and those will just be your losses, and that's going to go into your efficiency equation. Okay, so back to power in versus power out. Let's do some dimensional analysis. We know that power is mass times length squared over time cubed. Now I'm gonna wing it just for a little bit and see if I can derive this. So let's start with this. I'm just going to take a guess, and we already know that the power in. We already know that the more flow, obviously, the more gallons per second, the more cubic meters per hour, the more stuff we shove through there, the more powerful it's going to be. I'm just going to take a guess and say that that's going to be linearly related. So Q in, linearly related. And I'm also going to take a guess and say, okay, well, not a guess, but an educated guess, and say that the bigger that area is, the more powerful it's going to be. So let's look at that. So I'm just going to take a guess and say more flow times more area is going to give me power. I know that is in disagreement with this little equation, but let's just see where it gets us. So if I follow this out, I'm going to look at I'm going to be in mass per unit time, and then if I look at my area, I'm going to be looking at length squared. And now if I just keep going with that, I'm just going to end up with mass per unit. Oh, sorry, I screwed that up. Sorry, I said time and I wrote down length. So volumetric flow rate is mass per time. Area is length squared. So I've got mL squared over T. So I'm missing a what am I missing? I'm missing a T squared. Well, let's go back up. So I'm just going to say that's a dead end for now. I'm going to go back up to this guy and see if I can get it from pressure. So let's just say power in equals pressure times flow rate. And now pressure is going to be in force per area. And again, Q is going to be in mass per time. And if I take that, I know that force is mass times length squared. Area is length squared. And this is time. And I'm going to multiply that again by mass. I'm going to divide by time. And I think I'm in another little blind alley here. Let's just see though. Mass squared. The length squared goes away. I've got time squared here. What am I doing wrong? force per area, mass per time. Yeah, okay, I'm calling it a lifeline. I'm just going to go look it up. Normally I get that right on the first try, but let me, 'cause I know I've got a nice set of notes on it here.
Physics in several years. That's good to shake it out.
Like, I know I did this thing. Volumetric flow rate. Okay, so I see my error right away. I was just using the wrong definition for cube. I should have been using gallons per minute, like I've been saying all along, instead of kilograms per minute. So if I look at pressure times volumetric flow rate, let's just look at this guy. So here's power again. Obviously, it's mass times length squared divided by time cubed. If I go ahead and put in pressure, and again, I'd already written this out as pressure is mass times, well, it's force over, it's force divided by area. That's what pressure is. So, and force is mass times acceleration. So this L, do it so you can see it. This L right up here in the top, that's our length per time squared. Divide that by our length squared. That's pressure right there. And then here was my mistake. I was using mass per time. I should have been using some linear dimension cube times time. So let's go back to that. Okay, and in fact, I think what I saw you do there, Alice, was cross through the incorrect one.
Always keep it.
Yeah, absolutely. Always keep it there. So I'm just going to cross through that guy. I'm glad you reminded me of that. I'm going to cross through this guy. It was like, try one, try two. First you don't see, back to the back to the drawing board. No problem. So here's what we're going to do. I'll write it again. P in equals P times Q equals force over area. And then now, here's a critical one. It's length cubed per unit time. Okay, so now I think we're back on the right track. So again, force is mass times acceleration over T squared over L squared L cubed over time. I'll simplify, and I'm going to get mass times length to the fourth over length squared times time cubed. Simplify one more time. Mass length squared over time cubed, and there we go. Okay.
Okay, can you angle that a little bit more?
Absolutely.
So
Yeah, absolutely. Yes. Let me review that. So, neuralizer on the first two attempts. This is the this is the proper way to do it. And let me just where's my so I'll just review that one more time. So power is pressure times volumetric flow rate. Pressure is force in the numerator divided by area in the denominator. Volumetric flow rate is some volume, and volume is always length cubed divided by time. So now I'm going to march down here. Force, again, is mass times acceleration. Acceleration is length divided by time squared. Area is length squared, so that's still down here in the denominator. I'll just put a, oops. I'll put a 1. I'll put a 1 over L squared for my area. How about that? And then L cubed over time is just right there. So from here, it just becomes pretty simple algebra. So I've got mass times length times 1 times L cubed is just mass times L to the 4th. That stays in the numerator. Time squared times length squared times time is length squared times time cubed. That's down the denominator. If I then simplify length to the 4th divided by length squared, that leaves me with length squared in the numerator, and I've recovered the dimensions of power. So now I can say with certainty that power is in fact pressure times volumetric flow rate, and now we'll just need to figure out what those two are. All right. So with your design, are you expecting to have any kind of head in the device at all, or?
Nothing besides the river.
Yeah. Okay.
I mean, I think we're putting it on an off channel, so.
Okay.
I mean, it is going to have it. It's going to be an undershot design, not like a flat.
Right. Okay. Because there's another way. There's another way to do it. So now that we've understood that way to calculate power, and that's typically how a hydro dam works. Let's do it one more way. Let's do it one more way. Let me get back. Into another set of notes. Because in this case, it's not like you're not going to be able to measure pressure, first of all.
Yeah.
And you're going to have negligible head between the front and back.
Why can't you measure the pressure?
Well, we don't have the instrumentation to.
What would you use, I guess is my
Oh,
question.
sure. I mean, there are different types of sensors. There's usually some kind of piezo, some kind of thing that deflects or deforms. You might have just air on one side, water on the other, and depending on how hard it pushes or deflects,
Okay.
you'll be able to measure that, and so you'll convert that deflection of a membrane into a voltage, and that'll give you a pressure. But let's look at one other way to do it, and that's where I was going. But give me one quick sec to find those notes.
And can I get a copy of these ones?
Oh, absolutely. Yeah.
Excellent.
No, I'll put these right on the website.
And is it a Moodle website that you guys are using?
Yeah. Yeah. And I think we can get you access to it.
Oh,
I'd be,
I'd appreciate that, because then I can.
Moodle hates everybody.
Yeah, don't feel personally offended by Moodle. It treats everybody equally unfairly.
I
So
logged in my account, and the next time I tried, it didn't work.